Alright. Hi, I'm Kian, and I'm here to talk about TSP naive solution and TSP and colonial system. So, first of all, TSP a naive solution, we create an initial tour from 1 to the number of the cities, and we'll permute every possible combination of the tour to find the lowest one. And finally we display it. So here we are doing Burma 10, which is a 10 city problem by Burma 14, like the original one. So if we run it, this one is relatively fast, 2 seconds, find the best one. However, if we change it to 11, it will take a much longer time, so like about like 20 or 30 seconds. So why we are waiting for that to run, let's talk about ant colony system. So ant colony system is created by I believe Drogo. So basically it mimic like an ant colony in order to find the solutions. So uh, at the heart of everything is an edge. So an edge has a couple of others mm, parameter in it. So we have a distance, which is self-explanatory. We have pheromone. So pheromone is a desirability of each of the edge. So so we can calculate like the probability of like the edge will be chosen by using pheromone times 1 over distance to the beta. So and the update probability will be called whenever a glow update happening or local update happen. I will talk more in depth about it later. Um, so we have an edge table, which is like basically an interface to the ACS edge. So whenever a program need to be run, um, it will go through all iterations. It will release the number of n, which now is set to 10. Um, 10. So what happened is for every time a tour is created, it will check like check if like for the next tour. So the next tour will be checked by basically using a candidate list and just like have a probability to add it all together. Like do a bunch of stuff with probability and like calculate out a next city. So the average runtime of the thing is about O of n for every next city, and every time it happens, the edge will be updated to update the probability of it being chosen next and update the pheromone. Add to the tour, and it happened like until the tour is completed. So for each of the ant will be O of n of 2, O of n to the 2. And after all the ant have created their path, it will update like globally all the edges. So that will be O n squared, and so like the whole thing is O n squared. So after all the iterations have been done, all like the possible changes to the ant clone system have been made, it does a local search. So I'm currently using only two opt, which basically like change crossover, because 3 op is too time expensive. So after doing 2 op and everything, let's take a look at how it's run. All right. So same problem, done. So let's take a look at a more challenging problem such as Crow B100, right? There's a 100 side problem done in 2 seconds with 10 to 800. So if you compare it with the optimal value, which is 22 141, which is really close. Or let's do another one. Let's do a 400 problem maybe. Yeah. Yeah, let's do a RD400. Right. So RD400 is a 400 series problem. It will take a lot longer, but not by a lot. All right. So while I'm waiting for it to run, I will show you what I created. Right. So this should be what's this at? 134. All right. So so here is what I ran a bunch of problems. So as you can see, the runtime is actually pretty minimal with like 500 problems CDs from it only take 2 minutes, and with a lot of confidence in like how close it is to the optimal, like under 5% basically. And this is only with like 2 op. So if we are doing it with like 3 op, it can potentially be much better. And as I just show you, the runtime is polynomial order 2. Alright, so let's wait for this to run a little bit. Take a while. Alright, so this is a support class, finding a nearest neighbor. Very primitive. Alright, so this one. Okay, so this one is 24 seconds. Alright, 84 seconds. And it's a bit higher than the distance being put in here. The reason why is ant colony system is very randomly selected. So it sometimes it produces a little bit higher, sometimes it will produce a little lower. So like one of the ways that can help it is to run it like multiple times. Because remember that even if the iterations is there's a lot of iterations, but it ultimately shares the same edge and the same best. Alright, so a quick look at the nearest neighbor. Very primitive, very but it gets the job done. Let me show you how it will do if it is provided with like the problem of what is it? Random 400. Random 400. Random 400. It'll be very fast, but it will be like a lot higher. So it show so instead of like it will show like 1700, only this one is 1600. Alright, and that's it. Thank you for listening. My name is Kevin, and you just show my solution.